In this video, I'll discuss how to determine the ionization energy of hydrogen atom, limitations of Bohr's atomic models, the dual nature properties of electrons, and Heisenberg's uncertainty principle. Hey, I'm Teacher Tan. If you like my videos, do remember to click on the subscribe button below so that you won't miss any notifications when I update my channel.
What is the ionization energy of hydrogen atom from Lyman series? To know this, first you need to understand what is happening during ionizations. Electron in a hydrogen atom at first is at ground state n equals to 1. When energy is supplied, the electron will absorb the energy and move to higher energy level. For ionizations, the higher energy level here is referring to the n equals to infinity. When the electron is moved to n equals to infinity, it basically means that the electron has been removed completely from the atom and the atom now has become an ion. To calculate the energy required to move the electron from n equals to 1 to n equals to infinity, we can use the formula, which is difference in energy equals to the Rydberg constant multiplied with 1 over n initial square minus 1 over n final square. Initially, the electron is at n equals to 1. So, our n initial will be n equals to 1. Then, the electron is excited to n equals to infinity. So, our n final here is referring to the n equals to infinity. Then, by substituting these informations into the formula, we can get the energy required to excite one electron from n equals to 1 to n equals to infinity. And the energy required is equals to 2.18 times 10 to the power of negative 18 joules. Now, we look at the definitions of ionization energy. Ionization energy is the minimum energy required to remove 1 mole of electrons completely from 1 mole of gaseous atoms to form 1 mole of positive gaseous ion. In ionization energy, instead of removing 1 electron, we are removing 1 mole of electrons. So, how should we calculate the ionization energy or the minimum energy required to remove 1 mole of electrons? Remember, 1 mole of electron is equivalent to 6.02 times 10 to the power of 23 electron. Therefore, by equating 1 electron with the energy required to remove 1 electron from 1 atom, we then can calculate the energy required to remove 1 mole of electrons completely from 1 mole of atoms, and the energy is equals to 1,312,360 joule. We then can convert the energy to kilojoule, which is equals to 1,312 kilojoules. And this energy basically is the ionization energy of hydrogen atom. We then can write the ionization energy of hydrogen atom equal to 1,312 kilojoule per mole. Though Bohr's atomic model can be used to explain the light spectrum of hydrogen atom, it still has its own limitations. The first limitation is Bohr's atomic model can only be used to explain the light spectrum of single electron species such as hydrogen atom, helium ion, and lithium ion. The second limitation is the Bohr's atomic model cannot explain the dual nature of an electron. And the assumptions in the Bohr's atomic model stated that electron is orbiting in the fixed circular orbit around the nucleus is also arguable. De Broglie proposed the dual nature theory of an electron. De Broglie explained that particles such as electron possesses dual nature, the wave nature and also the particle nature. De Broglie suggested that light under appropriate conditions could behave like a stream of particles. Particles such as electron, when moving about the nucleus of an atom, also behave like a wave. Therefore, Electron has a wavelength, and its wavelength depends on its mass and velocity. De Broglie also came up with a formula to determine the wavelength of an electron. And the wavelength of the electron is equal to the Planck constant divided by the mass and the velocity of the electron. So, electron is actually a particle or a wave. If it is a particle, then it will behave like a rolling ball. We can determine accurately the positions, directions, and the speed of the electron. However, if the electron is behaving like a wave, then it is very difficult for us to determine the exact locations of the electron, just like we can't precisely determine the locations of a propagating wave in space. As an electron is not just a particle but also behave like a wave, therefore we cannot precisely determine the exact locations of an electron in space at a specific instant. Hence, Heisenberg came up with Heisenberg's uncertainty principle, stated that it is impossible for us to know simultaneously both the exact momentum of an electron and its exact locations in space. So what conclusions can we make? Basically, the Broglie hypothesis and Heisenberg's uncertainty principle could be used to determine the energy of an electron. However, both hypotheses and principles could not precisely describe the locations of an electron. To describe the locations of an electron, mathematical approach which involves probability is required.